Okay, next on our stop in Chapter 10 topics is going to be parametric equations. Okay, what happens with parametric equations is instead of x being defined by y being defined by x, or some blend of those two things, x and y are each independently defined by some other variable. Okay, that some other variable is known as the parameter, and the two common variables that are used are either t or theta. Typically, if it's a non-trig related set of parametric equations, the variable tends to be t. If the parametric equations tend to be trig related, then the variable typically is theta. So, for our opening examples here, it says, complete the table, sketch the curve given by the parametric equations for the given interval of t, and indicate the orientation of the curve on your graph. All right, so one thing that tends to happen with parametric equations, not always, is we're not necessarily concerned with the entire graph that could be produced by this, only by a certain piece of it. So we only care about the graph that goes from t values of -3 to +3. So we're not going to use any technology shortcuts, anything advanced here. We're just going to do this by like brute force, so to speak. What I have here is a table set up with the integer values of t from -3 to +3. We're going to take each one of those values, plug them into the x equation to get the x coordinate, take each one of those values, plug them into the y equation to get the y coordinate. So, when you plug the -3 in here, -3 minus 2 is -5. Plug in a -2, -2 minus 2 is -4. Plug in a -1, you get -3, and then just filling in the rest in the interest of time. Going to plug -3 into the y equation, so 2 times -3 is -6, -6 plus 1, -5. Plug in a -2, 2 times -2 is -4, plus 1 is -3. It's -2 minus 1, plus 1, sorry, is -1, and then just filling in the rest in the interest of time. Alright, so I'm going to plot these points here. So -5, -5. -4, -3. -3, -1. -2, 1. 3. 0, 5, and 1, 7. All right, now, very often, when we graph things normally, so to speak, we would extend that line up this way, extend the line down that way. But we're only interested in the part of the line that goes from a t value of -3 to a t value of +3. Okay, something else that's new that we haven't experienced before in the graphing world is to indicate the orientation of the curve on your graph. It's not just that set of points. It's, well, how did that set of points come about? Where did it start? Where did it end? So we always indicate going from smaller t values to bigger t values. So that was the first point, second point, et cetera, et cetera. So what we're going to do is put some arrows like this, and that will represent the graph of that curve going from that t value to this t value, indicating the direction of the orientation. Okay, another example, same story. We have a pair of parametric equations. The parameter is t. X and y are each defined in terms of t, and the t values we're concerned with here go from a -2 to a +3. So we have a table set up with the integer values going from -2 to +3 inclusive. So the -2, plug it into the x equation. That's positive 4 minus 1 is 3. Plug in the negative 1. 1 minus 1 is 0. Go through the rest. Interest of time, we'll just fill them in. This is an easy one in terms of doing the calculations. Each t value we're just doubling to get the y value. And then we're going to plot those points. So 3, negative 4. 0, negative 2. Negative 1, 0. 2. 3, 4. And 8, 6. And what we end up getting here is a parabola that opens up to the right. We don't want the entire parabola, so we don't draw it continuing this way, continuing that way. And they're specific that they want us to indicate the orientation of the curve. So starting at the point 3, negative 4, going to the point 8, 6, draw some arrows looking like this. Bottom of this page. Next thing they're asking us to do. For problems 1 and 2 above, eliminate the parameter in order to write the parametric equations as a rectangular equation. So for number 1, we have x is equal to t minus 2. Second one, y is equal to 2t plus 1. So what we need to do here is to write an equation. A rectangular equation just means kind of a regular, normal, an equation like we've done prior to knowing parametric equations. So one strategy for this is to take one of those two equations, solve for the t. So the top one definitely is an easier one to solve for. T is going to be x plus 2. Take that value, plug it into the other equation for the t. So we get y is equal to 2, x plus 2, plus 1. Now typically you're going to be expected to write this in whatever form would be the natural form you would write it in. So in this case here, we're talking about the equation of a line. So it would be expected of you to put this in slope-intercept form or something other than the way it looks right now. So this would be the more appropriate way of expressing your answer as a rectangular equation. Now, this would be referring to the entire line from here to here going in each direction, or going in either direction, not just from here to here. So very often what you're also going to be asked to do or expected to do is adjust this interval of t's going from negative 3 to positive 3 and rewriting it in terms of the x or whatever the appropriate independent variable is here. So we could just go by inspection of what it looks like on a graph, or what we could do is take this equation right here, x is equal to t minus 2, and that t value minus 2 is negative 5, that t value minus 2 is 1, and that would be our restricted interval for this rectangular equation, which produces the same parametric equation as above. Okay, number 2. Same set of instructions. We want to take this system, or this set of parametric equations, and write them in rectangular form, which means we want to get rid of the parameter, which means we want to get rid of the t. So the cleanest way to do this is I'm going to take the bottom equation, solve that for t. That can substitute in here. And then cleaning that up, the only thing we really have to do here is square out that 1/2 y. So x equals 1/4 y squared minus 1. That would be a very acceptable rectangular equation. Anytime you're dealing with parabolas that open left, right, having it in an x equals form is acceptable. Your book, in the earlier part of chapter 10, used that other form that it uses. If you wanted to write it into that would be fine, but this would be an acceptable final answer for that. Now, as far as adjusting the interval of -2 to 3, it would probably make sense to put that interval in terms of y, because that would be the natural, like what typically would be in like the x slot. Like if it was a y equals x squared equation, we'd want the x to be defining our interval. If it was an x equals y squared, we want the y to define the interval. So what we can do is use this guy right here, and our y's are going from -4 to +6. And you can check that on the graph. If you look at the smallest y value, it's -4. You look at the biggest y value, it's +6. So that would be our adjusted interval in terms of either the x, in terms of the x or the y, as opposed to being the t. A mistake there. All right. That wraps up part 1 of what we're going to accomplish today. Part 2 follows in a moment. Now we're going to talk about some calculator skills associated with parametric equations. All right, first place I'm going to go to is the mode button. Now we've been here before primarily to check whether we're in radian or degree mode. For what we're going to be doing for the foreseeable future, we want to be back in radian mode. And one of the new things that we are looking for here is, or we're looking at, is right below where you get to choose between radian and degree, there's function, parametric, polar, and sequential. Everything we've done in this class so far, most likely everything you've done in the graphing calculator period, has been in function mode. What we're going to look at now is, well, how does parametric mode work on a calculator? So we're going to want to choose that. One of the places where we get a significant differentiation is when you hit the y equals screen. Instead of being y1 equals y2 equals, etc., like it's always been in function mode, now it's set up to accept two equations that look like what we're given here. So if we want to put in this pair of parametric equations, we're going to use the xt theta n button. When you're in function notation and you hit this button, it automatically was an x. When you're in parametric notation, you hit that button, it's automatically a t. So it's going to be t minus 2, and then we're going to have 2t plus 1. So that puts in our first pair of parametric equations. Now, Zoom 6, the Zoom standard, is where you first learn how to graph basic, simple algebraic things. We've done a decent amount in this class where the Zoom 6 window works just fine. I'm just going to press that for now and see what we get. Well, in terms of just a rough comparison, it seems as though we got like a line with more or less the same looking slope, the same looking y-intercept. but it's extending beyond what we want, and it's not extending down as far as we'd like it to. So if we hit zoom 6, what kind of window does that give us when we're in parametric mode? All right, so we got some new things on the top here. We got Tmin, Tmax, Tstep. They were not there when we were in function mode because they weren't applicable to functions. Your calculator defaults from 0, and that 6.28 is basically 2 pi. Much of the applications that involve parametric equations are trig related. So that's why the calculator defaults to 0 to 2 pi. There's a decent amount that gets done with parametrics that is what you want it to default to. It just so happens to not be part of the first couple of examples. So that zoom 6 is going to default to a Tmin of 0, a Tmax of 6.28. Okay, the T-step. Your calculator defaults to that 0.13 number. I'm not exactly sure what that represents in terms of why that is what it is. But for most problems, that's pretty good. And we're going to experiment with, well, what happens if you change that in a moment? Okay, the other things, the Xmin, Xmax, Xscale, Ymin, Ymax, Yscale, those are the same things they've always been. There's no difference with those. So how do we adjust this to get what we want here, or from here? Well, the Tmin for this was -3. The Tmax was +3. And as I said, that default T-step that your calculator uses is usually pretty good. Okay, now I'm going to hit graph. So now that looks a lot more like what we want it to look like. Just on rough inspection, it appears as though it's where it needs to be, and it's showing part of the line it needs to show. Okay, if we trace it down on the bottom, you can see we're starting at t is equal to -3, which has the coordinates of -5, +5. Sorry, -5, -5. And up top, it's telling us what we're tracing. It gives us the pair of the parametric equations. And as you go to the right, you can see it gives you the t, the x, and the y for each one of those values that it's tracing on, all the way up to and ending at, I'm not quite sure why it doesn't trace all the way to the t is equal to 3. Maybe that's just a little quirky thing of the calculator. Let me double check my window. Yeah, going up to +3. I wonder if we need that t-step to be, let's make it a 0.1. And we'll hit graph and then trace. And maybe that gets us right to the 3. Maybe that's, yeah. All right, so let's take a look at the next one here. So I'm going to go back to y equals. I'll clear out those two equations. For this one here, my x is t squared minus 1. Didn't get out of the exponent there. T squared minus 1. My x is 2t. I'm going to go to my window. We're going from a t value of -2 to +3. That t-step of 0.1 is very close to that 0.13 number, whatever it was. And for tracing purposes, if we wanted to hit that very last endpoint, you might need a little cleaner t-step, and you're going to hit graph. All right. So that looks pretty good. Now, one thing that could be useful when we start to graph some of these, being that orientation of the curve is sometimes important to us, and they're asking us to mark it. When you're in a y equals, if you go to that symbol in color just to the left of the x1, if you press enter, we can change the color, and we can change what it does with the line. What we can do is have a little circle like that, and what we can see when that happens is the orientation of the curve. So why didn't it show me that then? Y equals graph. Did I not save it when I did that? Okay, so as it graphed it, we saw that circle showing where it is. And with a simple little graph like we just did right here, that's not really a big deal, so what? But when we get to some of the trig examples where sometimes you can end up tracing the same thing more than once, that's a useful thing to have that little circle go around. For now, I'll put it back to what it defaults to, just that straight line like that. Okay, graph, and it's back to normal. All right, next thing, let's take a look at what's the deal with that t-step. That 0.13 it defaults to, for lots of stuff, good enough. For that one problem we did, or maybe this one, I'm not even sure, making it a 0.1 instead of 0.13, got us a little bit nicer of a trace. Well, what if we just made it like 1? What would happen? Okay, what happens is it graphs it faster, but it's not quite as clear. It becomes a little bit more jagged. Zoom in on this too. You can see the parabola is not as smooth with that bigger t-step. Why is that not focusing? There we go. It kind of makes it a little bit more jagged. So what happens is you want to balance between, well, how fast is it going to graph it and how accurate is the graph going to be. Now, again, we're talking about one little tiny piece of a very simple parabola. So there's not a whole lot that can go wrong here. Like, this is a t-step of 1. So what if it's a little bit jagged? Nobody really cares. But what if we made it too small? What if instead of a t-step of that 0.13 or 1, we made it like 0.0001? What's going to happen here is we're going to get a super accurate graph, but it is going to take painfully long. Actually, it didn't even, that's too small. Let's do 0.001 graph. And as you can see here, it's taking a very long time to produce the graph. But in terms of as much high definition as we can get in a screen like this, it's going to be more accurate than it would be with a t-value that was larger. So we're going to graph some things in this class where we need to have a little smaller t-step than what the default value is in order to get a good looking graph, but we can't make it too small where we're staring at a calculator screen rather, like we are right now, waiting for the thing to finish graphing. So we're waiting. You can see it's got the little circle up there. When that stops going, it's done graphing. So it took quite a while for that to graph. So I'm going to put my t-step back to about a 0.1. Or if we just hit zoom 6, and then the window, it'll default to the t-value of min and max to be 0 to 2 pi, and at about 0.13 number. All right. That takes care of the next set of things that we wanted to talk about with parametrics. I'm going to do a time check and decide what is the next best thing to do. And we are looking at probably as far as we want to take it for day 1. If we were under normal teaching circumstances with a full 43-minute period and everybody in front of us, we would continue on with some other things. But I think for our particular environment, this is good enough for day 1 of parametrics, and we'll pick up with what comes next tomorrow.